This is the last section of Chapter 7. This is where things get a bit weird. We get something called the natural log and the number e, which is sort of like pi. It's an irrational number, but our first job is to figure out where it comes from. And to do that, we're going to go to back to our word problems about depositing money. And this is actually where people first discovered this number. So student deposits $500 into a savings account that earns 4% interest per year. How much does he have after 5 years? We know we've got this formula. We can do 1 plus the rate to the fifth power, and 500 goes in there. So we get 608.33 cents. Fair enough. We did problems like this a long time ago. But now so there's something called compound interest. Maybe you've heard of this, where interest can be kind of added more often, so you get more money. So if I said, I don't know why a student changed his name to Mark, but how much money would Mark, or student, same guy, have if his interest was compounded monthly instead of once per year? So that means we're going to take the rate and actually divide it by 12, because there's 12 months in a year. And then you do the 5 years times 12 months. So this changes from years to months, 60 months. So notice the amount comes out a little bit more. So compounding more often is a good thing for us, for the investors, but not so much for banks, because they're going to end up giving you more money. So then it came about, well, what if we could compound more often, like once a month, maybe once a week, or so we change the 12 to a 52, or maybe if we do it every day, we change it to a 365. And so our formula looks a little bit more complicated. We've got this n in there, so we divide the rate by n, we multiply the time times n. So Leonhard Euler is the one who came up with this, which is why some people think the number is called E, because his last name is Euler. So he said, let's compound as often as possible, but let's let r equal 0, t equal 1, and a equal 1 in this equation. So he ended up with this formula instead, 1 plus 1 over n to the nth power. And he said, okay, what happens if, this is where creativity and imagination come into mathematics. So he said, well, what happens if we let n become infinity? Class dismissed. Then we would start doing this. So compounding yearly, we're making n equal to 1. Half yearly or bi-yearly or semi-annually, n would be 2. Quarterly, n would be 4, and so on. And he just was calculating what number do I get? So 2, 2.25, then 2.44. Notice it's getting a little bit bigger and bigger. So then when I fill in the rest of the table, watch what happens. Monthly, we type in a 12, weekly's 52, and so on. Hourly, minutes, seconds, so I calculated. What is happening to the number on the right? 2.44, 2.69, 2.71. Notice it's getting bigger, but eventually it kind of tops out around 2.71828. Now, if we do this in the long run, I let that number become as close to infinity as I can, so that power and that number underneath the fraction, if I let that become like 999999999, out pops this magic number e, which is like pi. It's about 2.71828, but it keeps going on and on and on without any patterns. People have calculated trillions of digits. There's no patterns, just like pi. So this is important for compound interest. We call it continuous because it's like compounding every single second all the time. And it makes our formula a little bit easier, although most of the problems I give you, I'll tell you to use which formula, if it's continuous compound interest or if it's simple interest, which is what the problems we were doing before. So how much money would Stu have if his interest was compounded continuously? Notice it's a little bit more than what he had before when it was monthly, but not that much. So it really depends what the initial amount is and what the interest rate is also to see how much more money you're going to have in the long run. So now how are we going to use this in our class? This guy named John Napier came along and said, well, what if we take a log and we put the base as this number e? So log of base 2.718 and so on. And he said, let's call this the natural log. And you write it with ln. And on the calculator, it's the button that's right below the log. So we've got log base 10, and then we've got ln. So like if we do log base 10 of 10, we should get 1. But ln, or natural log of 10, is something different. Because this is taking this notation with the ln means the log is a base e. So these two are equal to each other. Log with a base of e equals natural log of x. Okay. So then what happens when we graph these two functions? Y equals e to the x. We take this number 2.71828 and so on and raise it to the power of x. And we take log with a base of 2.71828. Okay, we get something like this. And notice when I draw in this y equals x line, what do you notice? The symmetry. This point is mirrored over here. This point's mirrored over here. Well, actually, that's not a good point to pick. But it would be roughly over here. Okay, this point over here, and so on. So those are inverses of each other. Y equals e to the x and y equals natural log x. We're definitely going to use this fact. So natural log and e, we've just established. Natural log is the inverse of e to the x. So what happens when you plug in e into natural log? What do we get? Well, natural log means log base e. So if I plug in e to that, I should get 1. Because if I convert this to exponential form, this is the base, this is the power, and this is the output. E to the first power is e, of course. So natural log of e should be equal to 1. If we try this on our calculator, natural log, and e is right here above. So second e, and I always have to type in a number, e to the what power? So e to the first, that is just e, and I get 1. Okay, so that's an important result. Natural log of e equals 1. But what if I do natural log of 1? What do I get? That means log base e of 1. So then I convert this to exponential form. E is the base. To the what power would equal 1? Well, what's the only thing that could be? 0. Anything to the 0 power is 1. That's going to come up all the time if you haven't noticed. Anything to the 0 is 1. So we would say natural log of 1 is 0. This is another really important property or fact or truth. Natural log of e is 1 and natural log of 1 is 0. So let's take those things, and these are the kind of problems I'm going to give you. Solve these equations. If e to the x is 2.3, how do we know what x is? Okay, and remember, e is not a variable. It's 2.718 and so on to the x. Okay, so remember we had problems like this. We just did this where we need to get this power in the front. But what do we have to do to get the power in the front? We have to take the log of both sides. But we don't want to just use log and then put e to the x and then log of 2.3 because this x will come here, but then we have log base 10 of e. We don't want that. That's not going to help. So instead, we want to use natural log because natural log has a base of e, and that will cancel. If I do natural log of e to the x equals natural log of 2.3, then I move the x into the front, then I get natural log of e, and we just said that natural log of e equals 1. So we just get x equals natural log of 2.3. And now I can go to beast mode. Natural log of 2.3 is 0.8329. So I said 3 decimal places, so that 9 is going to bump the 2 up to a 3, 0.833. And now we can check e to that power, e to the power of 0.833 should be about 2.3. Okay. Okay, next one. If the equation has natural log in it already, then we need to figure out what this x is by raising e. It's called exponentiating both sides. E to the power of natural log x also will cancel this out. So then we just type into our calculator e to the negative 1.5. So e to the minus 1.5. 3 decimal places would be 0.223. And now we can check our answer again if you don't believe this is working. Natural log of 0.223 should be equal to about negative 1.5. Okay, and why isn't it exact? Again, because we're rounding. Okay, next one. If we see a 10 in the base, that's a hint to use common log base 10. If I take log of 10 to the x and log of 0.75, I don't want to use natural log or e because the base here is 10. The base is not e. There's no e going on in this problem. So then I get x times log of 10, and log of 10 is just 1. So that cancels out, and I get x equals log of 0.75. And remember, when I type in log, it's a base of 10. So my answer is negative 0.125. Negative 0.125. And I can check that. 10 to the power of parentheses negative 0.125. If I do a negative exponent, I should get fractions because negative exponents are not negative numbers. They are reciprocals. Okay, last one. 5 natural log x equals 3. So if I've got a number in front, I just need to divide first. So I'm going to divide that 5 over the other side. Similarly, if I had like 5 plus natural log x equals 3, I would just subtract this 5 on the other side. So get rid of numbers when you can. So then the next thing, if I have natural log x equals 3/5, I know that x must be e to the 3/5 because e is the only thing that's going to cancel this natural log out. It's the only thing that's going to make it go away. So then I go to my calculator, e to the 3/5 power, 1.82. 1.82. Okay, told you this was going to get weird. What happened to all the numbers? Okay, thanks for watching. Bye.